path? Or?
Yes, yes.
Okay.
That's correct.
I leave.
Okay, so welcome to this second paper, okay, in the test generation session of AST 2021. And the next paper is automated performance testing based on active deep learning. Okay, and the presenter is Ali Sedagatbaf, and he comes from the Rice Research Institute of Sweden. Okay, we will play the pre-recorded video as Ali is having some troubles with the camera, right? And after the video, he will be available for some questions. Okay, remember that the questions. Okay, you need to write down the questions on the chat.
Hello everyone, my name is Ali Sedagatbaf. I'm a researcher at Rice Research Institute of Sweden, and I'm going to talk about a solution for automated performance testing based on active deep learning. First, I will talk about performance testing and some solutions in this domain. Then I will provide some background information about conditional GANs and active learning. After that, I will explain the proposed solution, which is called ACTA. ACTA stands for Active Learning for Test Automation. Then I briefly discuss about the experiments that we have done and also the use of ACTA in DevOps settings. And finally, I will conclude my presentation. As you know, performance is one of the fundamental software quality attributes, which is crucial to guarantee functional correctness. To analyze performance, we generally have two approaches. In the first approach, we use a mathematical or simulation technique to model the system's behavior and analyze some performance measures like response time and throughput. In the second approach, we execute some test scripts on the system in order to identify the scenarios that would lead to the violation of performance requirements. A significant challenge in performance testing is to generate tests that will reveal performance issues within a short period of time. On one hand, we have several input value combinations and also configurations to explore, and on the other hand, we have a limited test budget. What makes this task even more challenging is that in most cases, we do not have access to the source code of the system. In the literature, we can find several exploratory performance testing methods. For example, we can use symbolic execution or fuzz testing to exercise different execution paths and identify the input values that would lead to the worst-case execution time. Evolutionary algorithms are another alternative when it comes to exploring a given space. But we are more interested in machine learning algorithms, which establish a model between the input space and the execution behavior of our programs. Among the machine learning solutions, PerfXRL and DN are the closest to the solution provided in this paper. PerfXRL is based on reinforcement learning, and DN is based on supervised learning. In PerfXRL, we have a test agent which continuously interacts with the system and tries to identify the input values that would lead to the violation of performance requirements as soon as possible. Experimental studies indicate that PerfXRL can identify those input values much faster than random testing. In DN, we have a discriminator neural network which tries to classify a given set of randomly generated tests into two groups: positive tests and negative tests. By positive tests, we mean the tests that will reveal performance issues if executed on the system. The ultimate goal of this neural network is to maximize the number of positive tests with respect to a given size for the test suite. GANs are a generative kind of neural networks which consist of two models: a generator and a discriminator. The generator plays the role of a counterfeiter and tries to generate fake data and deceive the discriminator. The discriminator, on the other hand, plays the role of a cop and tries to distinguish between real data and the fake data received from the generator. In order to train a GAN model, first we need to train the discriminator with real data. Then, in several iterations, our generator model synthesizes fake data and updates itself based on the feedback received from the discriminator. At the end of the game, the generator becomes so powerful that it can generate synthetic data that looks very realistic, so that the discriminator model is deceived. At this moment, we can use the generator model to generate several synthetic data which are very realistic. Conditional GANs let us apply some conditions to our data. Those conditions are usually expressed in terms of class labels. For example, if we have image data, those conditions could express the type of the entities that those images are representing. In ACTA, we use conditional GANs for test generation, such that conditions are used to express performance requirements. Active learning. The general hypothesis behind active learning is that if we let a machine learning algorithm choose the data it wants to learn from, then it can perform better than passive methods with substantially less data for training. So clearly, active learning is suitable for cases that data labeling is expensive. For example, software testing, where we usually have a limited test budget. A big question here is that how do we label our data? There are several scenarios that we can use for data labeling. For example, membership query synthesis is one of those scenarios that is suitable for cases that we want to sample data from a given distribution. Stream-based selective sampling is another scenario that is suitable for cases that we observe only one instance of data at each moment of time. In ACTA, we use pool-based selective sampling, where we have access to a pool of instances at each moment, and we need to select some of those instances for labeling. But how do we do the selection? There are several query strategies that we can use for data selection. In ACTA, we use least confidence strategy, where we select the items that our machine learning algorithm has the least confidence in their label assignment. Now let's talk about ACTA. As input, ACTA expects to receive the input space and performance requirements. By input space, I mean the set of input variables and the ranges of values that each of them can accept. For example, we may have floating point numbers, integer values, strings, and Boolean values. There is no limitation on the type of variables that ACTA can work with. ACTA expects to receive performance requirements in terms of some conditions. For example, we may have some threshold for each of our performance measures. As output, ACTA will generate positive tests. By positive tests, I mean the tests that will reveal performance issues if executed on the system. Model training. As mentioned before, ACTA relies on conditional GANs for test generation. Here, in each iteration of the training process, our generator model generates new tests by sampling from the input space and assigning a performance requirement as a label to each sample. Those generated tests will be investigated by the discriminator, which tries to verify the conformance of the labels with the corresponding data values. After that, we use the least confidence strategy to categorize our tests into two groups: uncertain tests and certain tests. By uncertain tests, we mean the tests that our discriminator has less confidence about the correctness of their labels. So what we do is we execute them on the system. The other group includes tests that our discriminator is certain about their label assignment. So we will use those tests directly for updating our discriminator model in the next iteration. This is called self-training, and self-training has proved to be an effective means for improving the accuracy of machine learning algorithms. In ACTA, we will start the training process whenever the accuracy of our generator model goes above a given threshold. To measure accuracy in each iteration of the training process, we easily compare the number of positive tests with the total number of tests generated by the generator. So when the generator becomes accurate enough, then we can ignore the discriminator and use the generator to directly generate a given number of positive tests for us. We have implemented ACTA using Python and the TensorFlow framework. The interface of ACTA is very simple and includes 4 methods. One method to submit tests for execution on the system under test. Another method for receiving the test outputs from the test oracle. And 2 methods for pre- and post-processing the test data. In order to evaluate ACTA, we have done several experiments on a benchmark web application called Rubis. Rubis provides the core implementation for an auction website, and it is widely used in the literature for performance evaluation. The input space of this application includes 4 integer variables whose value combinations reach more than 3 million data records. As a performance requirement, we expect that in all cases, the response time of this application is less than 1 second. In order to make our results comparable with those of DN and PerfXRL, we have made the same assumptions in our experiments. In fact, similar to the experiments performed on DN and PerfXRL, we injected 20 uniform bottleneck clusters into our dataset, such that each bottleneck would add 5 seconds to the response time of the application. At the end, we had approximately 300,000 bottlenecks in our dataset. Our initial experimental results indicate that ACTA is comparable with random testing, PerfXRL, and DN. As you see, for any size of test suite, ACTA performs better than PerfXRL and random testing. But it seems that ACTA is less scalable than DN. This is mainly because of the fact that in DN we have a retraining step in the test generation process. This step will be executed whenever the accuracy of the machine learning model goes below a given threshold. However, in the initial implementation of ACTA, we do not have such a retraining step. In fact, after training our SIGAN model and using the generator for generating positive tests for us, we do not do any retraining. Another fact worth mentioning here is that, as you see, we have ACTA in 2 modes, active and passive. In the passive mode, we had access to the whole input dataset, which includes more than 3 million records. But in the active mode, we initially have access to 1 million records, and during the selective sampling process, we label approximately 240,000 records. So the labeling effort of the active mode is much less than the passive mode. But as you see, their accuracy is very close. This fact highlights the benefit of active learning. In a DevOps setting, the goal is to continuously deliver high-quality software products. New changes are rapidly merged with the baseline product, and new versions need to be tested within a short period of time. In such a setting, we expect that small increments would lead to small variations in the set of positive tests. So we can reuse the previous generator model for the new version of the software. However, still it is possible that for some cases, the new version is much different from the old version. To cope with these changes, we add a monitoring component on top of the SIGAN model which keeps track of the accuracy of that model. And whenever the accuracy goes below a given threshold, the model will be updated using the active learning scenario that I explained before. In this paper, we introduced ACTA as a GAN-based performance test generator. ACTA is suitable for cases that on one hand, we have a large input space to explore, and on the other hand, we do not have access to the source code or the behavior model of the system under test. ACTA relies on active learning, which helps us minimize the testing effort. In order to evaluate ACTA, we have done some experiments on a small benchmark web application. However, we are planning to do more experiments with more complex applications and also try different alternatives for the query strategy and also the architecture of the network. Here you see the references to the papers that introduce PerfXRL and DN respectively. Thank you for listening.
Okay, so apologies for the trolls at the beginning. Okay, I was not aware that I was not going to see the video. Okay, here in the stage. Okay, so now there are. It's time for some questions. Okay, so we already have a question in the chat. Okay, so grammar-based fuzzers already mentioned in the chat. What do you think? How effective could be learning the input structure with deep learning instead of using grammars? Can it be integrated into ACTA?
Yes, I have to say that when we use grammars, we are specifying some rules. But in deep learning, we allow our machine learning algorithm to learn those rules. So we do not give some predefined rules to our algorithm. So we have to say that deep learning maybe can find more diverse input values than using grammars. But of course, we can use grammars to improve the efficiency of deep learning algorithms. I mean, it could be a good augmenter for deep learning algorithms.
Okay, thank you. And while others might ask some questions in the chat, I was when reading the paper, okay, asking myself some things. Okay, so were the tests that you're running in parallel or one after the other in sequence?
No, the tests are performed sequentially. Yeah.
And basically,
because because the machine learning algorithm needs to learn by interacting with the system, because it is following an active learning scenario. So it has to learn, for example, do some tests, learn from them, and then try other tests. So it has to decide, for example, what test to try next. So it has to know what are the results of the previous tests. So all of the tests are executed sequentially.
Okay, and basically the property that ACTA checks is whether the test lasted more than a second, right?
Yes, in the experiments that we have done on the Ruby's application, yes, we have only one requirement, and that requirement specifies that the response time of the system should be less than 1 second. But generally, ACTA can work with any sort of performance measure or any sort of conditions on those performance measures. For example, conditions on throughput, response time, CPU utilization, or any other measure that we are interested in.
And based on this approach, I was wondering because, okay, is there any tests, okay, that you could use, okay, that will really last more than 1 second because you injected basically some faults, let's say, okay, to make the system under test, okay, perform slower so that you could get some positives, okay? But in normal conditions, okay, this is something that happens or not?
Actually, this is a limitation to the application that we used for our experiments. This limitation is highlighted also in several other papers because the application is a very simple application with a simple business logic. So in most cases, the response time of the system would be less than 1 second. And another fact worth mentioning is that in order to make sure that our algorithm works properly, we needed to have a control over the, for example, the input values that lead to bottlenecks. So we injected some bottlenecks ourselves to see how the algorithm works. Yeah.
Okay, thank you. And you were saying that indeed we can use any property that we would like to use, like for instance, I don't know,
yes,
HTTP status codes or errors that might arise in the logs or whatever kind of a condition that might indicate that the system is not behaving as expected, right?
Yes, exactly.
Well, it's a very interesting approach. I don't have much experience with machine learning, okay, but I do have experience with performance testing, and it's always challenging, okay, to let's say think of several testing scenarios that might really put the system under some extreme conditions that might make the system under test fails. So it's really interesting. The work's really interesting, okay, because it could allow us for exploring, right, different tests that might put the system under these undesirable conditions that might make it to fail, right?
Yes. Thank you.
Okay, so I don't know if there are any other questions from the audience. No more questions, and thank you very much, Oli, for your presentation. Okay, and for the work you did. Okay, and I will switch to the backstage for the next paper to see if everything is ready. Okay. After the end of this session in 7 minutes, okay, you will be transferred to a discussion room where other attendants, okay, can join you, okay, if they want to ask some questions. So if you wish to stay there for a few moments, in case anyone wants to talk to you, please do that. Okay.
Absolutely, I will do.
Okay. Thank you very much.
Welcome.
So I will join the backstage for the next paper that's starting in exactly 7 minutes from now. Okay, and I will see if everything is ready for the next presentation. Okay, the next paper is a short paper. Okay, so I will come back to you in 6 minutes and a half approximately.